All right, get ready to dig in as we take a deep dive today, exploring the forces, those incredible geological forces that shape the planet we call home. We're talking aeolian and glacial processes. And, you've sent us some really amazing sources on this. We're talking textbook chapters, some really cool slides that break down different landforms. It's going to be exciting. So I guess our mission today is to go beyond just, simple definitions and really get a feel for how these forces work and the lasting impact they have on the landscapes that, we see every day.
And what's so fascinating about this is the massive range of timescales at play here. You think about it. Wind erosion, it's working. It's magic over millennia. It could be slowly shaping a single rock. And then you have a glacier that can just carve out an entire valley in just a few centuries. It really speaks to how dynamic our planet really is, even when those changes are happening over unbelievably long periods of time.
Okay, so why don't we kick things off with something a little, gentler. Let's talk about wind. When we talk about aeolian weathering and erosion, what are we actually talking about? It's not like the wind is picking up rocks and checking them around.
Right. It's more about, what the wind is carrying, those particles. Imagine a tiny grain of sand, right? But it's picked up by the wind and it's just constantly blasting against a rock face, for years, decades, centuries. That's aeolian weathering and erosion, in a nutshell. The wind wearing down and moving material.
Oh, wow. So picture yourself as that rock, just getting sandblasted for thousands of years. You'd look a little different. And this mostly happens in places where there aren't a lot of plants, right? Like deserts, for example.
Exactly. Deserts are a prime example. Coasts, too, where you have these open areas, even exposed river valleys, anywhere the wind can really pick up speed and there's not a lot of vegetation to, hold things down.
Yeah.
Without those plant roots anchoring the soil in place, wind has a field day, basically.
Yeah, that makes sense. Less resistance, more power to sculpt. But how does the wind actually move all that material? I was reading about different types of transport.
You're right. Particle size is really important here. The tiniest particles, things like dust, can get swept high up in the air, what we call suspension, and they travel at this incredible distances. We're talking sometimes across entire continents. Dust storms, right? Pretty dramatic example of this process in action.
No way. So that dust on my bookshelf, are you telling me that could be from, Africa? That blows my mind.
Right. It's totally possible. Then you've got, slightly bigger particles, sand grains, for example, and these move by saltation. They bounce along the surface, kind of like if you can picture skipping rocks, it's a little like that. And then finally, you've got creep, where larger particles are just kind of nudged along the ground, either by the wind itself or by the impact of those, those saltating particles.
I can't get over this. It's amazing to think that something as small as a grain of sand carried by the wind can create these mind-blowing landscapes.
Yeah.
And speaking of mind-blowing, those pictures of these wind-sculpted landforms in the research, they're incredible.
They really are something else. Ventifacts, for example, have you seen these? They're rocks, but they've been polished and sculpted by wind abrasion. And a lot of times they'll have these really beautiful, flat, almost polished surfaces.
I know, right? They look like they were made by an artist, not just natural forces. And those smooth surfaces, they actually tell us something, don't they? About the wind, I mean. It's not just random, is it?
You got it. You're thinking like a geologist now. Those flat faces, they're like ancient wind veins, basically. They reveal the prevailing wind direction from way back when. It's kind of poetic when you think about it, like rocks whispering secrets about past climates and weather patterns.
That's just, I don't know, that's just wild. Okay, what about those long, narrow ridges? They almost look like, I don't know, giant loaves of bread. I think they were called yardangs in what I was looking at.
Yeah, yardangs, exactly. They're a fantastic example of just how powerful wind erosion can be. It's like, imagine the wind carving out these valleys, but in solid rock. Sometimes they stretch for miles. They're like natural wind tunnels, basically.
Nature. The ultimate artist. Hands down. Okay, I have to ask about those mushroom-shaped rocks I'm talking about. The zeugens. I mean, they're kind of funny looking. How do those even happen?
So it all comes down to this process we call differential weathering. So picture this. You've got a rock, but it's made up of layers. And these layers, they have different hardnesses, right? Well, the wind, with its little sandblasting particles, it's going to erode the softer lower layer faster than the harder layer on top. And that's what gives you that classic mushroom shape.
Ah, okay, I see. So it's like nature is playing rock, paper, scissors, but with wind, hard rock, and soft rock.
Yeah.
Okay, and of course we can't forget about sand dunes. I mean, when you think of wind-made landscapes, that's what usually comes to mind.
And they're so much more diverse than people realize. We're not just talking like little bumps in the sand. You've got everything from these tiny ripples all the way up to towering sandhills. And every single one is sculpted by the wind. And if you know how to read them, each dune tells a story. The wind direction, how fast it was blowing, even the amount of sand that was available.
It's like a history book, but written in the sand. I love that. Now, the research also mentions something called loess. Is that just another type of dune?
It's similar, but here's the thing. Loess is actually soil, fertile soil, and it's made up of this really fine wind-blown silt and clay. And, you don't normally think of wind as a builder, but loess deposits, they can be insanely thick, like hundreds of meters thick in some places. And they make for some seriously fertile farmland.
Hundreds of meters. Wait, really? From just wind-blown dust. That's crazy.
It's wild, right? And those fertile loess soils, they're really important for agriculture all over the world. So it just goes to show you, wind isn't always about eroding and wearing down. It can actually build and enrich, too.
That's a really good point. We tend to focus on deserts and sandblasting. But these aeolian processes, they're fundamental for soil development, plant growth, even creating these little microhabitats for all sorts of creatures. The sources mentioned they can even influence entire ecosystems. It's like this reminder that it's all connected.
Totally. Think about the Grand Canyon, right? Everyone pictures that majestic canyon, and they think about the Colorado River carving it out over millions of years. And while that's true, wind plays a critical role too by subtly weathering those exposed rock faces, creating more cliffs and overhangs, and constantly reshaping the landscape in ways most people don't even realize.
Wow. So even this iconic landmark, which we associate with, like the power of water erosion, is also the product of wind. That just shows how persistent of a force it is.
It might be slow and subtle, but wind is a sculptor, a relentless sculptor. And its effects, they're literally everywhere if you know what to look for. But speaking of powerful forces of nature, how about we switch gears from the heat of the desert and those powerful winds to something a little chillier? Let's talk glaciers.
All right, bring on the ice. I'm ready. So what exactly is a glacier? I mean, it's more than just frozen water, right?
Oh, yeah, for sure. Glaciers are like rivers of ice, but they form when snow, falls year after year after year, and it builds up and it compresses and it recrystallizes under its own weight. So they're not static. They're actually dynamic flowing systems, kind of like icy conveyor belts moving across the land.
And I can only imagine how heavy these icy rivers must be. What is it that actually makes them move?
It's their own weight, really, combined with gravity, of course. That's the engine that drives them to flow outward and downward, kind of like a river, but in slow motion.
Okay, slow motion is an understatement, I bet. But how slow are we talking here? Do all glaciers move at the same speed?
Not at all. Some glaciers are slow crawlers. We're talking a few centimeters a day. But then you have others, like some up in Alaska, that can surge forward at meters per day. It's crazy. A lot of things affect their speed. The glacier's size, how steep the terrain is, even the temperature, it all plays a role.
Wow, so a glacier can be this slow, grinding force, or it can be like a speedy landscape or two. I bet all that movement leaves behind some pretty dramatic scenery. You have no idea. And, we can basically categorize all the landforms created by glaciers into two groups. You have the erosional features, carved out by the moving ice. And then you have the depositional features. Those are built up by the stuff the glacier picks up and carries along, and then eventually drops as it melts.
So we talked about continental glaciers, those massive ice sheets, but then we also have valley glaciers, which you said are like icy rivers. What kind of impact do they have on the landscape? Yeah, and you use the perfect analogy, icy rivers, and you're right, their impact is really different. Continental glaciers, like the ones covering Greenland and Antarctica, they're so massive, they can literally reshape the entire landscape underneath, carving out whole mountain ranges over, well, really long time. Valley glaciers, on the other hand, they're kind of stuck, in existing valleys, and they slowly carve them into those classic U-shapes that you see in a lot of mountainous areas.
So the continental glaciers, they're the heavy lifters, reshaping entire continents. And then the valley glaciers, they're doing the detailed carving, the finer work. Okay, let's dive into those erosional features. I'm picturing a valley glacier just slowly carving its way down a mountain. What kind of marks does it leave behind?
Well, you can almost think of these glaciers as giant ice scoops. As they move, they can carve out these incredible bowl-shaped depressions called cirque, and you usually find these high up in the mountains.
Yeah. I've seen pictures. They really do look like somebody just took a giant ice cream scoop to the mountain.
Exactly. Now imagine several of those cirques carving into a mountain, but from multiple sides over, a long time. Eventually, those cirques can actually sculpt these sharp, pointed peaks, and we call those horns. The Matterhorn in the Swiss Alps, that's a great example. It's a giant horn that was formed by several glaciers over, millennia.
Wow, they're dramatic. Those peaks are truly awe-inspiring. What about those thin ridges, the ones you sometimes see between glacial valleys? They're really narrow, like a knife's edge. Those have to be formed by glaciers too, right?
Yeah. They are. Those are called arêtes, and you're right. They're formed when you have two glaciers right beside each other, slowly eroding those ridges between them. It's like they're sharpening their icy knives. And what they leave behind are those super thin, jagged crests.
I know, I think they're beautiful, but it's also kind of terrifying at the same time. All right, so we've talked about what glaciers carve away. Let's shift gears and talk about what they leave behind those depositional features. What's the most, I don't know, obvious sign that a glacier was once sitting in a particular spot?
That would be moraines. Moraines are essentially ridges of debris. Think rock, gravel, sand, clay, basically anything the glacier has picked up along the way. It's like the glacier bulldozes all this stuff into a massive pile.
So basically a glacier's junk drawer. Like, it just shoves everything along and then dumps it out when it melts.
That's a great way to put it. The glacier's junk drawer. And, it's not just one big pile. You're right earlier. There are different types of moraines. You've got your lateral moraines, and those form along the sides of the glacier, kind of like icy sidewalks. And then you have medial moraines. Those form when two glaciers, they merge together and they create this stripe of debris right down the middle, like a seam on a shirt it is. And then, of course, there are the terminal moraines, and those mark the furthest advance of a glacier. It's like drawing a line in the sand, or I guess I should say in the till. It shows you just how far that ice once reached.
So it's like these moraines, they're like clues scattered all over the landscape, and they tell the story of a glacier's journey. What else do they leave behind?
Okay, picture this. You've got this smooth, elongated hill, almost like a giant teardrop, and it's pointing in the direction the glacier flowed. That's a drumlin. And a lot of times they're found in clusters. We call them drumlin swarms, like the glacier just had a bad case of the dropsies, I guess you could say.
Okay, that is a great image. I'm picturing all these giant teardrops scattered across the land. Now, what about those long, winding ridges? They're made of sand and gravel, and I remember seeing pictures they're called eskers, right?
You've got a good eye. Eskers, they're like the remnants of ancient rivers that used to flow within, or sometimes even beneath glaciers. As these subglacial rivers flowed, they carried all this sand and gravel, and that sediment was deposited. Then, when the glacier melted away, it left behind these kind of elevated, winding ridges. It's pretty amazing when you think about it. You're walking along an esker, and you're basically tracing the path of a river that flowed thousands of years ago, hidden beneath all that ice.
Okay, that is seriously cool, like a secret message from the last ice age. Now, I have to ask about those. You know those crystal clear lakes that you often see in mountainous areas? They're connected to glaciers too, right?
Absolutely. Those are called kettle lakes, and they form in a pretty dramatic way, actually. As a glacier retreats, big chunks of ice can break off and get stuck, embedded in the sediment around the glacier. When those ice blocks finally melt, they leave behind these depressions. And of course, those depressions fill with water, and you get these stunning, often really deep lakes.
So it's like the glacier leaves behind these little gifts, these pristine, crystal clear lakes. And then, of course, there are those vast flat plains, the outwash plains. Those are formed by glacial meltwater too, aren't they?
They are. Imagine a torrent of meltwater just rushing away from a glacier, carrying with it all this sediment. As the water slows down, it deposits all that sediment, and that creates these expansive, flat areas we call outwash plains.
Okay, we have covered a lot of ground here, from those windswept deserts to the icy landscapes carved by glaciers, and it is just incredible how these forces have shaped the world around us. But I think we'd be remiss if we didn't talk about the elephant, or maybe I should say the melting glacier in the room, climate change. The sources we looked at were very clear. Glacial retreat is a major issue.
It's a critical issue, no question. Glaciers around the world are retreating at an alarming rate, and it's mainly due to rising temperatures. And it's not just about losing these beautiful ice formations, although that's a tragedy in itself. This has far-reaching consequences for all of us.
So what are the consequences? What happens when glaciers disappear?
Well, one of the most immediate and significant impacts is sea level rise. When glaciers melt, they release billions, literally billions of tons of water into the oceans. And all that extra water, well, It causes sea levels to rise globally. This threatens coastal communities, infrastructure, you name it. Entire ecosystems are at risk.
It just, it really hits home that what happens in these seemingly remote, icy regions, it has a direct impact on the entire planet.
It's all connected,
Yeah.
absolutely. And it's not just sea level rise. The loss of glaciers also disrupts weather patterns. Glaciers, they play a critical role in regulating temperature and precipitation. When they disappear, it can lead to some really extreme weather.
It's like pulling a thread on a tapestry. You start to see how everything is woven together, and the consequences can be, well, pretty scary when that balance is disrupted.
Precisely. And we also have to think about freshwater resources. Glaciers act like natural reservoirs, storing massive amounts of fresh water in the form of ice. When they melt, those reservoirs shrink, and that threatens water supplies for drinking, for agriculture, for industries, anything that relies on that glacial meltwater.
It really is a sobering thought. These glaciers, they're not just there to look pretty. They play a fundamental role in keeping our planet healthy and balanced. Now, besides rising temperatures, are there other things contributing to glacial retreat?
Yeah, definitely. Changes in precipitation patterns are a big one. Some areas that used to get a lot of snow, they're seeing less and less snowfall, which means less ice is accumulating to replace the ice that's melting away. And then there's black carbon, that's the soot from things like industrial pollution and wildfires. This soot, it's dark, so it absorbs more heat. When it settles on glaciers, it actually causes them to melt even faster. It's complicated, a lot of factors, but a lot of them do come back to human activity.
So we're talking about this global issue, but it has these really local impacts, and it's all driven by this, interconnected web of human actions and these natural systems. A lot to unpack, but it's important stuff. Now, we've talked about wind, we've talked about ice, but there's another powerful force we need to discuss: gravity. You send over some research on mass movements, those gravity-driven events that reshape the Earth's surface. When I hear that, I immediately think landslides. But it's more than just landslides, right?
You're right. Landslides are definitely a type of mass movement, but it's a really broad category. We have rock falls, mudslides, even this process called creep, which is about as exciting as it sounds. But understanding these processes, it's not just about, satisfying our curiosity. This stuff can have a huge impact on the landscape and on human settlements, too.
Okay, so what causes these events? I mean, is it as simple as just having a steep slope and then like a little rain?
Well, slope angle is definitely a factor. The steeper the slope, the stronger that pull of gravity, and the more likely it is that things are going to start moving downhill. But it is rarely that simple. We have to consider the water content of the soil or rock, the vegetation, the type of geology. Even earthquakes and volcanic eruptions can trigger these events.
Wow, so it's this delicate balancing act, and when that balance is tipped, watch out. Can you give us some examples of these different types of mass movements and like how they actually play out?
Sure. Let's start with the slowest one. So slow you probably wouldn't even realize it was happening. Sediment creep is this really gradual downslope movement of soil or rock fragments. Imagine the earth just like really slowly taking a baby step downhill. You might see the effects over time, like a tilted fence or a tree trunk that's curved, but it's not exactly an action-packed event.
I love that image. It's amazing how something so gradual can still leave its mark on the world around us. What about something a little more, exciting?
All right, so a step up from creep in terms of speed and drama would be something called slump. This is when you have a mass of rock or soil and it moves downslope as a single unit, usually along a curved surface. Picture a landslide, but in slow motion. It's not as dramatic as a sudden catastrophic collapse, but it can still cause some serious damage and definitely reshape the landscape.
So instead of creeping, it's like the land takes a slow, sliding step downhill. What about the really fast-moving events, like the ones you see on the news, where, like, entire hillsides just give way?
Those are often mud flows or debris flows, and they can be incredibly dangerous. These happen when you have soil and rock, and they get totally saturated with water, often after really heavy rainfall, and then they just flow downhill. It's like a river of mud, and they can move incredibly fast, carrying everything with them: boulders, trees, you name it.
Yeah, I've seen videos of those, and they're terrifying. It's like they just engulf everything in their path.
And that's what makes them so dangerous. They can travel at speeds of up to 35 miles per hour, sometimes even faster, and they can travel for miles, just destroying everything in their path. And then, of course, there are rock falls, which are pretty self-explanatory. Rocks falling off cliffs.
Those seem like they'd be pretty hard to predict.
They can be. Rock falls can be triggered by all sorts of things. Earthquakes, heavy rain, even something as simple as a freeze-thaw cycle can cause cracks to expand and rocks to loosen, and then boom, rockfall. And that unpredictable nature, that's what makes them so dangerous, especially in areas where you have steep cliffs, and especially if there are people living or hiking nearby.
Speaking of dangerous, the research you sent over really highlighted avalanches as being a particularly hazardous type of mass movement. What is it about avalanches that makes them so different from other types of landslides?
It's the speed. Avalanches are these rapid flows of snow, ice, often debris, all mixed together, and they just roar down a slope. We're talking speeds of over 200 miles per hour, which is faster than most race cars. They are incredibly powerful, they're destructive, and they can be triggered by natural events like earthquakes or heavy snowfall, but also by human activity like skiing or snowboarding on unstable slopes.
Okay, 200 miles an hour. That is terrifying.
Wow.
So how can people stay safe in areas where avalanches are a risk? Because it sounds like they can happen really quickly and without much warning.
You're right. Being prepared is essential. I'd say the most important thing is education. People need to understand the dangers, be able to recognize avalanche terrain, know how to identify potential hazards.
So knowledge is your first line of defense.
Absolutely. And then beyond that, it's crucial to have the right safety gear. A transceiver, which can help rescuers locate you if you get buried, a shovel for digging, and a probe, which you can use to try and find someone who's buried in the snow.
It really drives home the point that you need to be prepared, know your limits when you're heading into those areas. But, all of this talk about these mass movements, these powerful events, it makes you think about the impact they have. We've talked about how strong they are, but how do they actually affect humans and, the world we've built? The sources you sent, they mentioned some pretty serious consequences.
Right, and it's right to take it seriously. These events can be devastating. We're talking loss of life, homes and businesses destroyed, infrastructure wiped out. Not to mention the disruption to transportation, communication, essential services, and the economic impact. It can be huge. I mean, the fallout from a single event can ripple for years. It affects communities long after the initial event.
It's a powerful reminder that these aren't just, geological processes happening out there in the world. They have a real impact on people, on people's lives. Makes you really understand why it's so important to be aware of these hazards, to try to mitigate them as best we can.
Couldn't agree more. We can't, stop these natural processes from happening. That's not realistic. But we can learn to coexist with them, to live with them more safely, more sustainably. That's where things like hazard mapping come in, early warning systems, even responsible land use planning. By understanding these hazards, where they're most likely to occur, we can make smarter choices about where and how we build.
It all comes back to that idea of working with nature, not trying to fight against it.
Yeah.
This whole deep dive, it's been incredible. We started with the wind, carving rock, then to glaciers, sculpting mountains, then the sheer force of gravity constantly reshaping the landscape. It's a lot to take in. So as we wrap this up, is there one big takeaway, one thing you really hope our listener walks away with after exploring all of these amazing, powerful forces that shape our planet?
I think you said it best, actually, when you called it a journey, because that's what it is. These processes, they're ongoing. They never stop. They're constantly shaping and reshaping the world around us. I think the key takeaway here is that the Earth is dynamic. It's constantly changing, even if we don't always see it, It's often too slow for us to grasp in real time. But once you really understand that dynamism, that constant interplay of forces, it changes how you see the planet. At least it did for me.
We have this tendency, I think, to think of the Earth as static, like it's fixed, unchanging. But that's the furthest thing from the truth.
Exactly. And when you realize that, it comes with a sense of responsibility, I think. We're not just passengers on this journey, we're active participants. Our actions, they have consequences, whether it's the way we build our cities, our impact on the climate, which then affects glaciers, weather patterns. It's all connected.
So understanding these processes, it's not just about appreciating a beautiful canyon or, respecting the power of an avalanche. It's about understanding that we have a role to play in this incredible, complex, and let's face it, sometimes dangerous system.
Absolutely. And I hope that, more than anything, this deep dive has sparked a sense of wonder, a sense of curiosity, because there is always more to learn, always more to explore and discover about this amazing planet we call home.
Well said. It's been an incredible journey, and I know I'm walking away with a whole new level of appreciation for just how dynamic our planet really is.
The pleasure was all mine, truly. Always enjoy getting to dig into these fascinating topics and, share the wonders of our planet with anyone who'll listen.
And to our listener, thank you, as always, for joining us on this deep dive. It's been a pleasure to explore these forces, these powerful forces that shape our world. And until next time, keep exploring, stay curious, and never stop asking questions about the world around you.